record my lecture and send you our whiteboard that way. So there's that. So I'm going to do a lot of sitting writing on this, talking to you guys. So that's how it's going to look for the foreseeable future. Again, hopefully I get a better setup. I will stop sharing that. Let me bring up. So yeah, this is hi. How's it going? This was unexpected for all of us. Yeah. So, also, why does the class start at 9:25? What are we doing? 9:30 wasn't good enough for you, Coastal? All right. All right, I'll shut the little door here. Why don't you try to do a class for a bit? I don't know how into are you this room right now. So how do I start my day? Having not one, but two students lie to me. It's great. It's great. Hey, my computer crashed during the exam, and I got back in and finished the exam. It's like, oh, that's interesting. Moodle says you only took 35 minutes to take the exam. Go on. Tell me more. Hey, I'm supposed to get 2 extra days on all my homework. Oh, really? That's not what this cheat says. Let me call people and find out. This is great. This is great. Okay, so I opened up the day. Let's get. Oh, Caitlin Evans, so big and boxy. Okay. Okay. So, I guess I need to have a syllabus. So I made one. That was pretty sweet. So let's share that with the world here. Hello, Zoom people. Please stop doing that. I don't want that there. I want that over here. Hey, syllabus. Look at that. Okay. Sorry. Okay. This looks a lot like the organic one you may have seen previously. We were running a little low here. Oh, can the people of Zoom, can the Black Box Society hear me? Thumbs up or something? I don't know.
Yeah.
Yes. All right. Excellent.
Yeah, I can hear you.
Excellent. Yay. Everyone can hear you. Yay. We're a big happy family on Zoom. All right. So, I'm not going to do actual office hours. Every week I will make a set of office hours that will go up in Moodle that are just Zoom links. You have to share them with regular organic, but no one ever comes, so whatever. They're there. Email. I heard you guys bought a textbook. I'm sorry. We're not going to use that textbook. It was $7. Okay. Well, then I don't feel as bad. I assume you watched my sweet YouTube video, right? So like, wear a face mask and shit. I think that's why I'm here. So yeah, classroom sanitation. I forgot to bring my little wet wipes, but wipe stuff down, whatever. All right, class objectives. So I've taught a version of this class once 10 years ago. I'm old. So we're kind of using some of that stuff. So I look at this as if you were leaving and going to graduate school, what stuff would you want to know when you started as an organic chemistry graduate student? To help me in this, I've emailed 2 former students of mine that are currently second and third year grad students and been like, what are things you wish you would have known when you left here that you didn't, that you know now, that I could like reasonably teach? So I'm going to go over some uses of transition metals in organic chemistry. If you've taken advanced organic, we're not getting that deep, but I will show you how stuff works from an organic perspective. If you ask me if there's a Jahn-Teller effect, I'll go like, sure. Sigmatropic rearrangements, Aldol reactions, amide couplings, basically, and then I covered my bases with and more. But I think there's gonna be a whole section on olefin oxidations that I just totally forgot to put on here. But whatever. I'm gonna show you how to search the chemical literature, and we'll kind of work on how to read through a paper and like extract the important stuff, like the general structure. You'll pick up on that as we do stuff. So the searching chemical literature thing, that was what the SciFinder thing was for. So not on campus people, which I guess are less of you, more of you than I thought. I was told last night at 8:30 that the link to register for SciFinder works if you're off campus now. I did not try because I had stuff to do. So if you try that and it works, awesome. If it doesn't work, I'll have to yell at people until it works. But I would like you to do SciFinder.
Dr. Wakefield,
Yes, ma'am.
this is Caitlin. I tried doing the SciFinder thing last night, and I live off campus, and it didn't work for me.
It said like
So
IP, like unauthorized IP address.
Yeah.
Yeah. What time did you try it?
I want to say it was probably like 9 or 10.
Okay, because I got an email at like 9:30 that was like, "Yo, it works." So I'm gonna have to be like, "Yo, it doesn't."
Maybe I'll try it again.
Yeah.
It worked when I got on campus.
Okay, well that's good.
Yeah.
But like that's fine for like you, but Jonah is not on campus, so I've got to figure out how to get it to work for him, which has been like my concern. So, it says exam 2. It should be exam 1 because like, well, whatever. So I guess we're gonna do like 2 exams and a final. Do I know what the structure of these exams is gonna be? No. We'll figure it out. Everything's gonna be like take home, I guess. I don't know. Okay. Sorry, I'm really selling this right now. So in regular organic, since I have people that are at home and in class, I just made the exam online on Moodle. I can't do that in this class. Like it just won't work for like what the tests need to be. So like we're gonna have to like work on like the honor system that like Team Black Box and Jonah's like got a camera going, but Team Black Box and Jonah can like do an exam and like send me the finished product, and you guys could do the same. The only way I can kind of do that and have it be fair, which is like a big thing for me, is to just make them take home exams because I can't like proctor an exam for you guys, and like I don't want to like watch Jonah take an exam on a camera. That just seems weird, right? So it's just be like, yo, here, figure it out. So that is the plan as of right now. Whatever. Yeah, you probably need more time than that. So how we're gonna do this is like we're doing it now. There'll be Zoom people. There'll be people. This is my big out. If this goes to hell, and we have to close campus, or whatever, I will try to maintain like synchronous times, but I might end up just recording lectures. I just want to give myself that out because I also don't know like what people's internet situation is going to be if they like have to go back to whence they came or whatever. So I'm just trying to give myself that. I will try to maintain like an actual class, but not 100% sure that'll be doable. If like I decide to take the tiny human out of daycare or just do daddy daycare all the time, it'll be hard to daddy daycare and lecture. I mean, we can try, but let's like partway through it might be like, I gotta feed this baby. 1 second, let's discuss amongst ourselves. So I'm gonna record everything. I will do my best, like I said in the email, to put them on YouTube. It takes a lot to like take a class and like edit it into a semi-functional like YouTube video, and I'm already doing that 3 times a week. So I'll do my best. I mean, I could put up something really rough, but we'll see. But with that being said, this is a smaller class. I'll probably just leave it so like I'm just using my computer mic, which will then probably pick some of you guys up. So like if you don't want to be like YouTubed, I can come up with something else. But like with such a small class, I think it's just easier if like you can hear them and stuff. Since there's only 3 or 4 people, that is a snake in a box. Like no, literally, it's like a big like taxidermied like snake. It's like 7 feet long. See what you miss when you're like at home? Giant taxidermied snakes in glass boxes. Um, so if anyone has like a severe aversion to their voice finding its way onto YouTube, let me know and I can like try to do something else. Moodle, we got a Moodle page. We got one thing working. So there's already stuff up. There's the first set of slides that I don't know how long those slides are. I don't know if that's like a day's lecture, a week's lecture. I don't know. We'll find out. So grading, I just ran back the 500-point thing. Exams, 200 points. Homework is 100 points. Do I know what homework's going to look like? No. Final exam, 100 points. Project, I have a grand idea. It really hinges on SciFinder. So we'll see. Happy little 10-point grading scale. You good? Homework assignments I'll post up on Moodle. If you're in person, you can just give them to me. If you're not in person, I don't know, scan them, take a very nice cell phone picture and email it to me. I don't know, something. Again, this isn't a real semester. This is all fake. None of this is real. It's like the simulation we live in broke, and like, this is what we ended up with. So, I have a grand idea for a project. But as I said, if I can't get everyone on SciFinder, it's probably going to have to go away. But we'll talk about what the grand idea for the project is here in a second. It will involve a short presentation via Zoom or something. All right. So what I have to decide is the following. So, in graduate school, we used to do this thing called Molecule of the Month, which was we would pick our advisor would pick a molecule, where we would vote on a molecule. Who voted? And then everyone in the group would break into smaller groups and propose a synthesis of that molecule. And then would like go through SciFinder and look up reactions and precedent to say like, oh, hey, this works because of this reaction that's already been done by someone in this reaction. And then we would present them, and they would be judged based on like creativity, feasibility, number of steps, right? All this stuff. And so I thought that would be a good way to like use the information that we have here, or that you get here, is either one of two ways. Either one, everyone picks their own molecule and proposes their own synthesis of their own molecule, or we go with the like one molecule for the group, and then we break into smaller groups and like we pit it against each other to see who can come up with the coolest, best, most feasible synthesis using all this cool knowledge that you now have. So, but if I can't get SciFinder for the 4 people that aren't on campus, that makes it way harder. Or it's not fair to be like, hey, one person in the group can't use SciFinder and can't look stuff up, and other person has to carry them on their back like Dora the Explorer carries a backpack. Right, that's not cool. So we're gonna give this SciFinder thing a few days, see if we can like work out the bugs, and then we'll figure out if you have a interesting use of your knowledge. So I don't currently have a book for you. What I am currently drawing from, because I haven't really opened this one yet, is these 3 books here. So, The Art of Writing Reasonable Organic Reactions, Classics in Total Synthesis, and the Strategic Application of Name Reactions in Organic Synthesis. So I've taken a reasonable amount from the name reaction book right now, and I'll steal some stuff out of classics and the art book. I'm not saying in any way, shape, or form you need to buy these, but we're gonna do a lot of switching Zoom, people. I'm sorry. Like, we're just gonna figure this out as best we can. It's not gonna be always pretty, but it will be as I get rid of it for poor Jonah. All right, and share. Haha. All right. So steroids, right? You have did I spell that right? This is your general structure of a steroid. Right? You will get the occasional story time. I know the faculty member who drew it. So there is a faculty member who's now super famous who's giving a talk, and someone asked him to draw a steroid, and he started drawing his steroid from the D ring to the A ring, and the famous faculty member who asked him to draw the steroids got flustered because he was drawing his steroids backwards and walked out of the room before the person he asked the question to could answer it because he drew his steroid backward. Organic chemists aren't the most socially well-adjusted people. So these are steroids, and there's this whole class of molecules called furanosteroids, which I'm going to try to get us a real class one day, a real classroom. I promise. Where you stick a furan steroid, where you stick a furan between the A and the B ring. What that does is it puts a lot of strain on the A and the B ring. It pulls those rings closer together and starts to bend all of the bond angles in the A and B ring, and it puts a lot of strain because those angles want to be like this, but having the furan bends them closer together. That furan pulls them closer together. So the whole reason we made thiocyanate is sulfur's bigger than oxygen, right? So the thought was, if we put a sulfur in place of the oxygen, carbon-sulfur bonds are longer than carbon-oxygen bonds. Sulfur itself is bigger than an oxygen. So that would relieve the strain in the A and the B ring, right? If the A and B ring are strained because you've pulled the molecules closer together, you've pulled everything closer together, if you put a bigger atom in there, you should relieve the strain. The reason we cared was for one particular furanosteroid called wortmannin. I'm not going to make you draw the structure. I think it's in the paper. And it binds to PI3 kinase. Right, we're getting biology down here. And it binds to it by reacting with a leucine, so the free nitrogen on amino acid. That nitrogen adds to this carbon and pops that ring open. The problem is, little medchem for you. If you have an enzyme that's important to you being alive, if you destroy that enzyme, if you covalently bond something to it so that enzyme can't work anymore, you kind of die, right? Because if your body has to spend a lot of energy to make an enzyme, right? And then if you take something that just renders that enzyme useless, right? That's not good because then you got to devote all this energy to make that enzyme again. And usually inhibitors to enzymes or things, right? Usually drugs are reversible inhibitors. They will go bind to the active site of an enzyme or a target, come off, go back on. So you tamp down the activity, but don't just totally eliminate it. Wortmannin is an irreversible inhibitor. It binds to the enzyme and never comes back off. Right? So it totally kills the enzyme. So we were trying to develop a drug based on wortmannin that would go fit in the pocket that Wart Mannan fit in, but then wouldn't bind to the enzyme irreversibly. So we thought, okay, let's see what happens when we put a sulfur in here as opposed to an oxygen. So helenaquinone is much, much simpler than Wart Mannan. Much simpler. So that was like, we can do this on this simpler molecule that has this same core, right? They both share this kind of structure. And we can see what happens when I put a sulfur in here in the simple molecule versus when there's an oxygen, right? Because like I would probably still be trying to make Wart Mannan if that was my graduate school project, as opposed to this, which I was able to actually finish, right? So that's why we wanted to make this switch, is we wanted to see what happened when we made this one atom change. How does it impact how basically nitrogens add to this molecule? All right, so let's, more sharing. Boom. Boom. Hopefully Zoom people see a slide though. All right, so that was my 20s, and I just went through the paper that I sent you, and I looked up every metal that was used in this synthesis. Now, some of them were, kind of cheating. Like this sodium was just like the counterion on borohydride. Didn't really do a whole lot, right? But everything else actually was involved in doing a reaction, like interacted with the organic parts of the molecule to do a reaction, right? And like the whole class could probably just be going through all of these reactions, for all of these metals. I don't want to do all of them, right? I want to hit the highlights, I want to hit the high points, right? So, hey now, computer. So, I want to look at lithium, palladium, and ruthenium. So, I want to talk about a particular type or class of deprotonations with lithium. I want to talk about palladium cross-coupling reactions, which these are kind of the backbone for modern synthesis. Like, if you were to work in a pharmaceutical company and had to make drugs, the way they make a lot of drugs is they make them using palladium cross-couplings, at least in the early stages. And then ruthenium, we're going to talk about olefin metathesis, which is another super useful reaction. It's won a Nobel Prize, so the palladium cross-couplings. It's like used in polymer chemistry, it's used in total synthesis, it's just used broadly. So I'm gonna kind of work through the synthesis and go through the steps, and then when I get to a step that I want to kind of expand on, we're just gonna take a little detour and talk about that reaction in more depth, and then cycle back to the synthesis. So now I did the number one thing I hated as a student, which is when the professor just cut stuff out of the PDF that he sent you. I did not have time to draw all this stuff. One day, next year's class, it'll all be drawn. But I basically spent 5 to 8 hours on Saturday and Sunday doing slides for this class. So I had to find spots somewhere. Right? So do you remember when we had organic what was organic 1? Yeah, organic 1. One of the first things we talked about in synthesis was the concept of retrosynthesis, right? This isn't quite that, but what I'm showing here is this is the thing I can start with. This is the thing I can buy, right? So this is what I'm going to start my synthesis with. Typically, when you see the 2 arrows on top of each other, that's just kind of indicating there's a whole bunch of steps. So we start with thing we can buy. we do a bunch of steps, and that gets us here, right? And so this is, 60%, 80% of the molecule that you want to make. We get to this kind of like, this is a key structure, where once we get to this, we think we can make it the rest of the way. And then again, more steps, and we get to this. Right? So not so much retrosynthesis and working backwards, but it's more like, here are the things that I think are important. Right? The thing I'm starting with, kind of a key intermediate, someplace that I'm trying to get. He's carrying stuff. Not a classroom.
Okay. Just tell Michelle.
Okay, I gotta find a room, which is, not great.
Or you can just ask her.
I usually have to just find a room myself. But okay. I'll figure it out.
I won't be back until probably tomorrow.
All right.
I've got 6 hours of testing.
Don't get the Rona. All right. Goodness, last words. Right. So here I'm just highlighting the three, like the two structures that I think are important along the way. Oh, I forgot. Did everyone? I haven't checked. Did everyone pick a day for lab? I gotta know. You might be Thursday because there was only one Wednesday day left when I looked last. Oh, so it's the all-girl Wednesday lab. Excellent. I'm totally outnumbered. If there's a mutiny, we know what happened. All right. Wash it over there.
Sorry.
Yeah, now, man, you cough and people just duck under a table. They're like, shit, not today.
I had an asthma attack yesterday in class, and Agbo was just staring at me like he was going to kill me.
He said to you, no.
He's a little insane about some things. We're not allowed to touch the spray bottle, the sanitation. He has to touch it for us.
Interesting.
What?
I have a whole bunch of disinfecting wipes I gotta put in my bag so I can wipe down my little area.
Well, he doesn't let us touch anything.
Okay. So some of these reagents you will recognize, some of them you will not. We will talk about them. It'll be fine. It won't be super scary. So on Moodle, I have put a PDF document that is just, I think, 4 or 6 pages of abbreviations. So that when you look at a paper and you see TBS, you can be like, I feel like Wakefield taught me this, but I forget. So then you can just go look it up. And you won't tell me because I did teach it to you and it will hurt me too much. All right. Wait, so I have a whole big list of abbreviations for you to so you don't just feel like everything's just a bunch of letters. You can actually go kind of get a sense of what things are. Okay. So we're gonna work through this slide because it has 2 things I want to talk about. And the first is something called a lithium halogen exchange. So, in this first step from 10 to 12, this paper is 12 years old, and I was going through it, and I realized there's no number 11 in it. I was like, oh my god, what a horrific thing to realize 12 years later when you can't fix it. I was like, oh god. So lithium halogen exchange, we're going to go over here in a sec, but it's when you, as the name implies, you take an alkyl organolithium and treat it and add it to something that has a halogen, and your lithium will replace that halogen, and you end up with a carbanion. So we're going to stop share, then we're going to reshare, hopefully. Reshare? Uh-oh, I lost Zoom. Oh no, rookie move, we lost Zoom. Sorry. Sorry, Zoom people, I lost you. Don't leave me, Zoom people. Oh man, and then Jonah just gets put on the projector. I'm sorry, Jonah. Hi, everyone. Don't worry, like, between my crappy projector and, like, your lighting situation, you're just a silhouette. You could be anyone. All right. So, what's happening here in that first step? So you have the two bromines. Then you add N-butyl lithium. Right? And what happens is the lithium will replace one of the two halogens. And so if you remember my little line from organic, right, that lithium is positively charged and that carbon is negatively charged. Right, so I'm not doing a deprotonation with the NB lithium because it's a strong base. It normally would deprotonate stuff, but it will switch. But instead, it will just kind of switch places with a halogen. And then, so that's the first part of that reaction is making this carbanion. And then it says you add, then it says then acetaldehyde, right? So you make this acetaldehyde is this aldehyde right here. So then you're able to add your carbon to this. And then we work it up with water or acid to make the alcohol shown. So it's a reaction that you don't know in the lithium halogen exchange, right? But then it turns into effectively like a Grignard reagent or any other like carbanion organometallic adding to a ketone or aldehyde, right? It was like I try to get in your head like, oh hey, if you have a Grignard reagent and you add it to an aldehyde, you make a secondary alcohol. Well, I have a carbanion, right, an organometallic, adding it to an aldehyde, I still get a secondary alcohol. This is the same kind of principle. It's just how you get to that carbanion is different. So, I have two bromines, why did I just take one off? So there's a few reasons. One, you can control it with stoichiometry, right? If I add one equivalent of N-butyl lithium, I only add enough N-butyl lithium to react with one bromine, right? So I got that going in my favor. And then two, this molecule is pretty small, and it's hard to put multiple negative charges on small molecules, right? You can do it, but it is difficult. I'll show you an example in a second, right? Especially when they're going to be side by side. So once one bromine comes off, and you make that negative charge makes it harder for you to take the second bromine off. Because you don't want to have -2 on your molecule. And the way this is set up is you make this first. And you make all of this with your N-butyl lithium, and you wait for that to be formed. Then you add your aldehyde. So that way, all your N-butyl lithium's gone now. So when your stuff reacts with the aldehyde, there's no butyl lithium left to then go react with the bromine. It's a little bit easier to take off now that negative charge is further away, right? So the order in which you add stuff combined with stoichiometry and kind of how the molecule wants to behave makes it so you only do one. Back to the slides. Feel bad for the Zoom people. We're just like flipping around. Feel bad for you guys because usually it'd be like a board I'd stand at. So my brother teaches, and he has a whiteboard set up in his guest room, and he has this high-end 4K camera, and so he can stream. We got the black boxes again. Sorry, black boxes. And he can stream. I did it again. Oh no. 2 slides or 1 slide? Zoom people?
2.
Damn it. Every time. We're going to figure it out. We're going to learn. I'm old. Technology frightens me. So he can like stand at his whiteboard and actually use a whiteboard because he has enough resolution on his camera that you can actually see it. I love you, Mac, but I don't think we're quite to that point. We barely have enough resolution on this PDF that I copied. Sorry. So then, next step is PCC. Everyone remember PCC? PCC oxidizes alcohols to aldehydes and ketones. So I have a secondary alcohol. I'm treating it with an oxidant, PCC. PCC also has chromium in it. That's where I got chromium in as a metal. Right? So that oxidizes it to a ketone. And then I use N-butyllithium again and ethyl triphenylphosphine bromine or bromide. So this is, remember we talked about making Wittig reagents? This is a Wittig reagent that just needs to be deprotonated. So we're going to switch again. We're just going to go back and forth. I'm sorry, if we come up with a better way to do this, you can tell me. But like I want to like show stuff and draw things. Sure. Yeah. So that is triphenylphosphine. Oh, that's a really bad 3. Right, this is a phosphodium salt. So we can just buy this. And then you add a base. Right, let's make a generic base. I used N-butyllithium. And then that base removes a proton, pushes electrons over, and you make an ylide. Do you remember it's an ylide because it's phosphorus plus carbon minus. It can exist as this thing with 2 charges. Right? That's what ylide means, is that it has 2 charges. Right? And this is a Wittig reagent. And this is able to turn aldehydes and ketones into double bonds. And if you remember, I was like, hey, it's always way better to use an aldehyde than a ketone, because aldehydes react way faster. We did not have that luxury when we did it this way. So this takes a while. I forget exactly how long. And you make, right, so step 1, step 1, you did that oxidation, and you made this ketone. Step 2 was you took that phosphorus ylide and you made this double bond. Now the way this double bond is drawn in the paper is a little weird. It has a little squiggly line and it has a little arrow and it says like 2-to-1. So what that little squiggly line shows is that you have a mixture of isomers. You'll see these squiggly lines on double bonds when you have a mixture of E and Z, or cis and trans. You'll see it on chiral centers when your chiral center is a mixture. So this arrow, the little squiggly line, or the little squiggly line here, means mixture, right? So whenever you see a line like that, whatever kind of stereochemistry it is trying to denote is a mixture. Sometimes it will be, the ratio will be noted, sometimes it won't, sometimes it'll be in the text. That's what a little squiggly line means. So for this, I had 2/3 of my stuff was, checks brain, the E isomer. This was the 2. And then 1/3 of my stuff was the Z isomer. Right, when you use ketones, you often will get mixtures of E and Z. It's not like aldehydes, where if you use an aldehyde and a monosubstituted Wittig reagent, you always get the cis isomer, right? With ketones, you almost always get a mixture. Because while there is a difference in size between in this case, didn't say it, the thiophene, that's what this is called when it has a sulfur in it, the thiophene and the methyl group, right? It's not a big enough difference in size for the reaction to pick one isomer over the other. So I'm not going to go into the mechanism for this yet, but you make a 4-membered ring. You may remember from organics the oxaphosphatane, but you have it kind of, that 4-membered ring kind of has axial and equatorial positions, just like a chair. And so when the reaction happens, it will prefer to put the bigger group equatorial, the smaller group axial. But they're not as clearly defined as in a chair. So even though these are different in size, it's not like one's massive and one's tiny, then it messes up then you get a mixture of which one's axial and which one's equatorial. Okay, so that gets us there. Quick, try to share the screen for Jonah correctly this time. Did we do it? I think we did it. Somewhere Jonah is happy. All right, so then this is the second, and then here's a second lithium halogen exchange, where we do the same thing that we did before, but instead of adding acid aldehyde, we add DMF. Does everyone remember DMF? Other than the fact it's a polar aprotic solvent? Okay. And then that makes an aldehyde, and then we reduce that aldehyde with sodium borohydride. How I stuck sodium in there on my list of metals. Right. So let's go over this and kind of show you how this works. This is sadly not the smoothest, but what are you going to do? We live in like a hellscape now. So, all right. Look at Evan's back. Wakefield's so depressed. All right, again, NB lithium, we're just going to remove our bromine and add a lithium, right? And then DMF looks like this. All right, so dimethyl, NN-dimethyl formamide, right? Form, like from formaldehyde, is just the the smallest aldehyde is C double bond O with 2 hydrogens formaldehyde. And then you will add this to the carbonyl carbon. And this kind of works like when you add things to esters at low temperature where they get stuck partway through. So when you add this, at negative 78 degrees C, this isn't super stable, but it is stable enough that your lithium binds to your nitrogen. It makes this little 4-membered ring. All the letters in the word stable. All the letters. And this will be stable at negative 78 degrees C. So as long as we keep this cold, this little 4-membered ring doesn't fall apart. Which means I only add one of my carbanions to DMF. Because when this warms up, so I add the DMF, all my lithiums react with one DMF. And then when you warm this, when it warms, these electrons come down, take out the nitrogen. You warm it, you have to add a little acid. All right? And then that will make you an aldehyde. Right? But you used all of your nucleophile, you used all of your organolithium doing that first addition. So when you add the acid will destroy any lithium that's laying around and then allow your little 4-membered ring to fall apart to make an aldehyde. So you've made this aldehyde that would be reactive, but you've gotten rid of everything it can react with. So now you can isolate that aldehyde and then do the second step, which is turning that aldehyde into a primary alcohol with sodium borohydride, which you guys all totally know from organic too. So now I need to share this. It's so hard. We're figuring it out. Okay. So we have 14 that has 2 carbons beside the sulfur, right? And what I end up doing is from 14 to 15, I take one of those hydrogens and I turn it into a TMS group, trimethylsilane. So how am I able to select for one of those hydrogens to be removed and not the other, right? Because if you think about their pKa, like how acidic they are, they're pretty much in the same place, right, in the same environment, so they should be roughly have the same reactivity. In the way that we're able to select for the hydrogen that's on the side of the OH and not the hydrogen on the side of the double bond is the OH actually directs where the N-butyllithium reacts. So the oxygen on the alcohol coordinates to the lithium on the N-butyllithium and kind of holds it, and then holds that butyl group close to the hydrogen that gets deprotonated. So this is called a directed lithiation. So the 2 lithiations we're going to talk about in a little more depth. We're going to talk about lithium-halogen exchange, and we're going to talk about directed lithiations. Right, in this part of the synthesis shows both of those. So what happens is alcohols are way more acidic than a vinyl carbon, even a vinyl carbon beside a heteroatom. So we add excess N-butyllithium, and it removes the hydrogen from the OH, and then that now more negative oxygen binds to a positive lithium that's attached to a butyl group, holds that butyl group near the hydrogen that you want to take off, and you take it off. And then you add a mixture of TMS chloride and triethylamine to add the silyl group. Now, silicon likes making bonds to oxygen more than it likes making bonds to anything else. And so what actually happened here is you would put a silicon group on both the oxygen and the carbon. And then the 5% citric acid was, you just need to make it ever so slightly acidic, and it would cause the silicon group on the oxygen to fall off and leave you with the silicon group on the carbon. Now, these are the things you don't get if we're doing another paper, the one that I didn't do, which is that reaction worked about 70% of the time. The other 30% of the time, it would take both silicon groups off, and I will have wasted an entire day of my life that I would never, ever, ever get back. So I have distinct memories of going, ah, and hitting my hood after I took the NMR and there was nothing there. I spent an entire day turning 14 back into 14. And I was like, oh, my life is pain. Why is it like this? Right? So you had to be careful when you added the acid, because if it got too acidic or it stirred too long, it would take the silicon group off the carbon. Right. Next step is just a simple alcohol protection, right? TBS chloride, imidazole, and then DMF as the solvent. You took the OH and made it into a TBS group, because now I don't want that OH around, right? We talked about protecting groups being a thing that you use to hide reactive functional groups. And we needed the OH to be reactive with N-butyllithium in the last step, because that let it direct where that deprotonation was going to go. But now we don't need that thing to be reactive anymore, because we need to take the final proton off. Right? You pull that proton off of, 16, right? Again, N-butyllithium and ether. I was very creative. I used the exact same reagent and conditions 4 times in one slide. We did it. I used to buy N-butyllithium in like 1 liter bottles. Right? And then we do the DMF trick again, which is again going to get us right to an aldehyde. And then I added a Grignard reagent. Here's where I got magnesium in. And that got to a secondary alcohol. Okay. So a lot of the stuff you kind of should have a vague recollection of from good old Organic 2. Now, I understand that most of you took it during the last semester. So, sorry. I did my best. It was rough, man. Right. So I want to talk about, like I said, 2 sequences. I want to talk about the lithium-halogen exchange and then the directed deprotonation. So there are a bunch of lithium reactions, but these are the 2 that are probably the most frequently used, that you'll see most in synthesis. And I just want to talk about how lithium-halogen exchange works and then how directed deprotonations work. I'm not used to seeing people write. It's so weird. No one's ever around. I taught a class for 2 people. 2 in-person people last Friday. 2. So like, I could have just stayed home. You could have stayed home. It's been great for all of us. No, I had to kill the planet and drive here. Alright. So, lithium-halogen exchange reactants. Okay, so we use an alkyl lithium to replace a halide ionic compound with a lithium. Now, I did a quick tertiary search of like the mechanism for this, and they were like, under debate. And I was like, cool, not teaching it. So you're lucky. So the goal of, you'll find I'll talk about molecules like they're people. The goal of the organolithium in this reaction, it has motivations, has desires, right, is to make the most stable organolithium it can. Right? So you can measure stability kind of based on like pKa's. You think about which one of these anions is most stable. That is the one that you're going to form. So if you if you remember your pKa's, even like roughly, I don't remember the numbers, but here I'm gonna just quick hot swap in here. One second, I'll be right back to it. Don't worry. But if you remember pKa's, right? Simple hydrogens on alkanes have pKa's of around 50, right? 50 is not very acidic, right? Or basically not acidic at all. And then hydrogens on vinyl hydrogens on double bonds, that's like 40-ish, 45-ish, somewhere in there. So more acidic. And then hydrogens on an alkyne, I think that's like 30, 28-ish, somewhere in there. Right? So when you do these reactions, you will use an alkyl organolithium, something that was made from a group or a molecule that wasn't very acidic, right? So this is really reactive, less stable, and it's going to react usually with a halogen that's on a double bond or a triple bond, and it's going to make something that is more stable, right? The negative charge on the double bond is more stable than the negative charge on just the straight chain, right? So an sp3 hybridized carbon that has a negative charge is less stable than an sp2 hybridized carbon, is less stable than an sp hybridized carbon. So the trick is S character, right? So this is sp3. This is 25% s orbital. This is sp2. This is 33% s orbital. This is sp. This is 50% s. The more s character a carbon has, the better it can hold on to. Sorry, that is not right. sp is up here. Sorry, I was just going across, not thinking. Right, 25, 50% s. The more s character your carbon has, right, the more of its electrons kind of reside in the s orbital, right? The more closely they're held, the more easy it is for that carbon to be negatively charged, right? So even if you don't remember pKa numbers, right, you can remember just like, oh, this is an sp hybridized carbon. It's easier to be negatively charged than an sp3 hybridized carbon. So we typically start out with a carbon that is sp3 hybridized that has lithium on it, and then we're pulling a halogen off of something that is sp2 or sp hybridized, because they don't mind being negatively charged as much. How we doing so far? No one has like dropped the class like during the class, so this is good. I'm sure you looked at these slides when I sent them out and was like, "This is not what I signed up for. What the hell is this?" All right, so let's go back to our slides. Yay! All right, so like I said, you proceed to make the most stable organolithium, and basically you're making the thing that can best be negatively charged. So if you just looked at, like I said, if you looked at all the hydrogens, it's like, oh, I'm going to remove a halide that would come off of the thing that's most acidic, right? So alkyne, then alkene, then aryl. So those are pretty similar, right? They're both sp2 hybridized, right? If it's on a double bond or on a benzene ring, or in this case, a thiophene. Right? And then alkyl groups are the hardest to remove a halogen from because they make the least stable anion. For the most part, we're going to use alkyl lithium reagents, right? So the different organolithiums have different reactivities. The most reactive is tert-butyllithium. This is the one I'm sure I told you in organic one briefly, that if you put it in a syringe and squirt it out in the air, it will shoot fire because the tert-butyllithium reacts with the water in the air so violently and so exothermically that it then sets itself on fire as you squirt it out. Then you have sec-butyllithium, then N-butyllithium, and the term N is like old-timey. So N stands for normal butyl, meaning that it is straight chain. Okay. Class goes to 1040, correct? But I won't keep you too long. Okay. And then methyllithium is kind of the least reactive of the bunch. The difference between the butyls is the number of carbons on the carbon that's negatively charged. Right? So if you remember when we talked about, I'm pulling a lot of stuff from Organic 1 and Organic 2, but we talked about carbocation stability, we said that, hey, carbon is slightly electron donated, right? Carbon gives electrons to the carbons around it. If you're a carbon that has a negative charge, the last thing you want is your buddies giving you more electrons, right? So tert-butyllithium has 3 friends around it pushing more negative charge onto it. So that makes that carbon even more negative and even more reactive. Tert-butyllithium has 2 friends pushing electrons towards it. So it's getting more electrons than it wants, but less than tert-butyllithium. N-butyllithium has 1 guy giving electrons, and methyllithium has no friends. Lives in the woods by himself. No one loves him. It's really sad. Right? So the more hindered, the more groups coming off of the negatively charged carbon, the faster that is going to react. So tert-butyllithium will kind of replace a halogen with a lithium in like all situations, and we'll do it the fastest. And then as you get less substituted, you become a little more selective and a little bit slower, and the substrate scope goes down a little bit. So we're going to see an example about another reaction where they do a lithium halogen exchange using tert-butyllithium, and they replace a primary halide, just like an sp3 primary halide, with a lithium, because it would much rather be straight chain with a lithium than tert-butyl with a lithium. So it's still working on that, which one is more stable. Tert-butyl is way less stable than having a straight chain. Okay. Also, when you get on Wikipedia for tert-butyllithium, at the bottom of the page is a story that I tell you guys about the girl in grad school who set herself on fire with tert-butyllithium and died. Like, tert-butyllithium has a really bad publicist. It's like, here's what the reagent does. It killed someone. It's rough. She was wearing so these bottles are all sealed, right? So when you get a bottle of tert-butyllithium or N-butyllithium, they have a septum on top, so that when you open the bottle, you never open the bottle, right? You have to stick a needle through the septum. But you also have to put nitrogen or some inert gas in, so that when you pull the liquid out of the bottle doesn't go under vacuum, right? Because if you take 10 mils out, you've got to put 10 mils of something back in to make up that volume since it's sealed. Well, in her group, they were like, oh, just like put pressure on it, not just backfill it, but actually push on it so it makes it so you can take it out easier. Well, she was doing that, and her syringe fell off her needle, and so then it was just nitrogen pushing at high pressure in to backfill, but now there's no syringe on it, so it just pushed, or no syringe on the needle, so it just pushed like in a whole bottle of tert-butyl lithium out the needle onto her. It then catches on fire, and she was wearing a fleece jacket, which then got all melty. No good. And we're going to end on that happy story. Congratulations, everyone. Don't you want to be an organic chemist now? This is great. I'm going to try to find us a room with like desks and actual seating. I will do my best, but 25 live is terrible. So if I can find a room, I went through like 7 or 8 rooms in Edwards and found nothing. So I'll start looking in Wall, and hopefully I'll have a room by Thursday. If not, we'll be back here. If I get a room, I will let you know.
And did you get my email?
I did. When did you send it?
Yesterday.
I must have missed it.
Okay, so my class ends on October 6th.
Oh, yeah, that one. Yeah, that's cool.
Okay. I just
So-
figured that might make it easier.
I think there might be 1 or 2, if we're good, bye Zoom people. I think, where's my stop share? I think that there might be 1 or 2 reactions that could benefit from just like doing it one day and then like working it up the next. But for the most part, I don't think it's like going to be a huge deal.